So my name is Krzysztof Pietroszek, and I am a director of a game research lab at the California State University and a recent graduate of the University of Waterloo. And this work was done with Dr. James Wallace and Dr. Ed Lank at the University of Waterloo Human-Computer Interaction Lab. And I will be talking about tiltcasting, which is a 3D interaction technique for large displays that utilizes mobile devices. So here is the motivation of my research, of our research. Well, we see more and more 3D content displayed on large displays, be it in a public or in semi-public settings. And as you see, even in this session, most of the interaction with displays is done as a direct interaction that is from close proximity of a display. But sometimes display might be put high up or does not have the direct interaction. And especially in 3D context, when there is a 3D content displayed on a large displays, a direct interaction is not necessarily the best way to do it because of eye convergence and other issues like stereoscopy from close proximity of the display. So the alternative is to use at a distance interaction. And here we have an example of a game which we are designing in our lab in which children are supposed to help Little Red Riding Hood to select objects that are hidden in a 3D environment behind rocks, bushes and leaves. And traditionally, this kind of interaction would be done with special input devices, Wiimote or Leap Motion, or it could be done with a 3D tracker, a magnetic tracker, or motion tracking devices like Vicon. But what we did already in our previous research was to show that a mobile device can actually act as a very efficient 3D interaction device because it has all the characteristics which are necessary to turn it into a 3D interaction device. It is always close to user, it has a data connection, it has motion sensors, camera and mic and touchscreen. So in previous research we designed a technique that was called smart casting, and it was shown that this technique performs on pair with a specialized input devices for 3D interaction. In the current research we're interested to take this a step further, that is to show that the interaction can be actually done in a way using all the modalities of the mobile phone that outperforms traditional 3D interaction devices. So here comes the design of a tiltcasting. A tiltcasting is a technique in which we cast a 2D plane into a 3D control space, and we control that 2D plane using the tilt of a phone. And the moment when the phone cuts through, the plane cuts through a 3D object, the object becomes selectable. So we are really selecting objects on a 2D plane. And this is done by absolute mapping of a cursor position on a touch screen onto the 2D interaction plane in a 3D space. Now, there are some important characteristics of this technique. First of all, the selection is done by releasing a finger, not tapping. So that reduces a Heisenberg effect. And also, there is an occlusion removal mechanism that is whatever objects are in front of the plane disappear from the view. And I will talk about it a little bit more in detail. So this technique addresses 3D interaction challenges which we identified, which needs to be addressed by a 3D interaction technique to be effective for any 3D content or 3D environments. The first one is occlusion. So if a user is asked to select an object that is occluded from a view, we have a problem which has to be somehow addressed by occlusion management mechanisms. And there is many mechanisms developed for occlusion management, but most of them require either to divide the selection phase into two separate phases, or it slows down the selection in some other way. So there is a cost of having selection on occluded objects. Another issue is target disambiguation, which happens in dense environments. So let's say we have objects which are close to each other, and we use a traditional technique such as a ray casting. When we cast a ray from an input device, this ray might cut through more than one object, and then there has to exist a mechanism of disambiguation between which object we're actually interested in selecting. And then the final problem which occurs on non-stereoscopic displays is depth identification problem, which is the question where the object really is on a depth, on a z-axis. So if you look at this picture, maybe you see on the right picture that the red sphere appears to be closer to us and the blue sphere is actually appears to be further. But in fact, if you look at the camera position, the red sphere is further from us and the blue sphere is closer to us. And that is the depth illusion, which is a result of not having any depth Q in the 3D environment. So surprisingly, tiltcasting addresses all three issues just by the fact that there is a plane tilting in a 3D space. So the first issue, the occlusion, is addressed by the occlusion removal mechanism, which I mentioned. That is that any object in front of the plane is removed temporarily. So this way you can very quickly scan through the 3D control space in search of the object you are interested to selecting. And then you can come back to your view by putting the plane in the vertical position. The depth identification also happens naturally for the tiltcasting because the plane provides a natural perspective cue, which is one of the strongest indicators of depth. So, for example, as you see on the picture on the right, if we, on the top right corner, we don't see what is the position of the blue spheres. We are unable to say where they are on the depth axis. But when we start to tilt the plane, we see that the top object is in a specific position in a 3D, and we know where it is because we see the perspective of the plane cutting through this object. So it gives us an idea how far from us the object is. And finally, the target disambiguation is partially addressed by the fact that we can only interact with objects which are cross-cut by the 2D plane. And this way we are really dealing with an issue of disambiguation on a 2D dimensional plane instead of 3D space, which is reduction of the complexity of the problem. So to see how the system actually performs, we performed an experimental evaluation comparing tiltcasting with our previous technique, smart casting. And the reason why we chose smart casting as a comparison was because smart casting was already shown to perform on pair with input devices for 3D interaction, and also it removed the confound of having a different device, and we basically use for both techniques, we use a smartphone and we see which one is performing better. Also, as in smart casting and previous studies, for example by Vanneken in 2007 on dense 3D environments, we designed the study in the same way, so it's a replication of a study of Vanneken, so we can compare the results between different studies. So the 3D environments in which we evaluate our system was the following. In the middle, you would have a yellow sphere that was also always placed in the middle of a screen and on the zero axis. And then it was surrounded by 43 occluders or distractor targets which are rendered as blue spheres. They are randomly distributed. And then we have a red target that is of different sizes. And this target is kept at the equal distance from the yellow object, which is in the middle, equal 3D distance. That is, it is basically rendered on an imaginary sphere surrounding the yellow sphere. And the selection task was to select first the start object and then as quickly as possible, but also precisely select the red target. For our design, we had, as you see, two interaction techniques, two target sizes to have two different levels of difficulty, indexes of difficulty. We also tested if actually stereo or non-stereo rendering has any influence on the performance. We suspected that maybe stereo will be better because there is no issue of the depth identification. And we also had the two target visibility conditions. That is the most important condition because, as we know from previous research, occlusion slows down the selection very strongly. So in our study, some targets, red targets, were not occluded and others were fully occluded. So the results were quite positive. What we found was that smart casting, that is an implementation of array casting on a smartphone, performed similarly to plane casting. So even though qualitatively we can see that it was, tiltcasting was a little bit slower, I changed the name from playcasting to tiltcasting recently, so I get confused. So tiltcasting was a little bit slower, but not significantly slower on the selection of non-occluded objects. And this is quite interesting because if you think about what is raycasting for non-occluded objects, it is really a 2D selection. You have objects which are not occluded, so you really need to manipulate only the X and Y position, and Z position does not matter because we are selecting the first object which is intercut with a ray. And in our case, the tiltcasting is always a 3D selection because we are manipulating a plane in a 3D. On the other hand, the selection of occluded objects showed a significant improvement on the tiltcasting. So in tiltcasting, the performance was much better. It's actually not that different between the selection from non-occluded and occluded objects, which basically means that occlusion did not have an influence on our results, so that we can basically select any objects in 3D regardless if they are occluded or not, which is a significant result. But also interesting were the results of our TLX data. So while there was no significant difference on the performance on the non-occluded objects between smart casting and plain casting, even though there was this added cost of tilt casting on the non-occluded objects, there was an actual huge difference in the performance, in the user preferences for tilt casting when we have the occluded objects. So occluded objects were much easier, less frustrating, required less effort. People felt like they had better performance. They were physically less demanding and mentally less demanding to be selected using tilt casting. So this is a short paper, so we are planning to do future studies on this technique. First of all, we want to deploy the technique in public settings. It was only evaluated in a laboratory setting for performance. So now we are designing this Little Red Riding Hood game and to see if actually the users are preferring the tilt casting over other techniques in ecologically valid study. We also think about the generalization of tilt casting for mass interaction. That is in situations in cinema, for example, when you might have 300 users interacting with single large display, and that cannot be done with direct interaction. And also optimizing tilt casting for target-aware environments, for example, by finding a best tilt position which casts through most targets, a best camera position which we didn't address at all yet in the study, and for example zooming, or using some other techniques for target awareness, which would maybe improve the selection time. So thank you very much, and I will take questions if you have any.
Come to the microphone if you have a question. Please give your name and your affiliation. Questions?
I may be.
You're able to have too many keys for being a question. All right. So I have a question. So how well do people understand what's going on when this view, it's tilting down and it's getting this perspective view? Is that something that they basically intuitively grasp, or do you have to explain?
Yeah, it's surprisingly easy to grasp. We did short training to see if there is any learning effect, for example, and we found that after 5 trials, people were proficient, first of all, in this. There was no difference, but they also immediately grasped it. So there was a sentence of explanation. We also tried not to explain and just say, try to select some objects, and they get it immediately. It's probably due to the fact that it is a natural, the moment you hold the phone, you move the plane, so it's immediately you make this mental connection between these two planes, that they are related.
Maybe go to the back one. Might help.
It works. Hey, I'm Martin Bressler from CTU in Prague, and maybe this is a stupid question, but have you tried to use some gesture to change the point of view? Because just a small change of the point of view could help to recognize which object is further and which one is closer.
Yeah, so there is a lot of research on changing the camera position to deal with occlusion. That addresses one type of occlusion and only in some types of environments. So if you have objects that are not dense enough, so the camera changes actually will show the object. And if occlusion is only that object is behind some other object. But if objects are inside other objects, then changing camera position to any position doesn't matter because they are contained. But this technique addresses that because you cut through this occluding object.
Yeah, I understand that. But maybe these two things could be combined because you are tilting the phone just in this axis.
Yeah.
So you can use the other axis to make this small change of the point of view, and it could just help to recognize this.
For sure, and we actually tried more than one axis of movement of both plane and the camera, and it looks like the preference of the users, which was also a little bit surprising, was on one axis. That might be because there is some research showing that the less degrees of freedom, the less mental demand there is on the technique. So maybe it would be beneficial to add the camera movement on the other axis. We can try it.
Okay, thank you.
Yeah.
Last question?
Hi, I'm Rofe from University of Maryland, College Park. So I saw you did stereo rendering in your experiment. So I'm wondering how stereo rendering helps user to select the object faster or slower. And are you using 3D glasses, or what kind of techniques are you using for stereo rendering?
Yeah. That's a good question, and there is details on it in the paper. I just didn't have time to go to it. So stereo rendering did not improve and actually hurt some situations. And we were also surprised with it. We used a passive polarized screen, so it was not an active screen. Maybe that's the reason. It's because the screen was of 55-inch size, and for smaller screens, the 3D effect is not that good. It was on a LG TV, but it did not improve. At least for tiltcasting, we attributed to the fact that we already have the perspective cue, so it doesn't actually matter that you have a 3D. It still works, and for people, some people don't like the 3D because it hurts their eyes. So basically, they prefer not to have a 3D and have the perspective cue.
Yeah, and I think maybe the NVIDIA 3D Vision toolkit might be a good choice for future experiments. Okay, thank you very much.
Thank you.
Thank you very much.